So the idea for sampling is the following. We're really asking the following question. Can a continuous time signal be exactly reconstructed from a sampled version of the signal? So we have this continuous waveform, and we're just going to pick out samples at particular discrete times. We're going to store those in a MATLAB vector, and we want to know, can we get that original signal back? It's going to be an infinite MATLAB vector, okay? Can we get the original signal back exactly? Can you tell me what the value of that signal was at any point in time? And the answer turns out to be yes, provided that the signal is band limited, meaning that it has a maximum frequency beyond which the transform is equal to 0. And that's the first requirement. The second requirement is that you have to sample it frequently enough. And the sampling rate has to be at least 2 times the maximum frequency of that signal. And this result that says that this is possible is what's referred to as the sampling theorem. So for those of you who come over to CMRR, if you went to the auditorium the other day for the discussion, there's a statue of a guy out there. That's Claude Shannon. He's one of the people who is given credit for this, recognizing this, along with Nyquist, who you might have heard of. Okay, so what's the idea behind sampling in the continuous time setting? So the way I described it was we took a continuous time signal and we took the samples and created a discrete time signal. We're not going to quite do that here. Okay, we're going to get to that eventually. But what we're going to do here is we're going to take a continuous time signal and convert it into a train of continuous time impulses. The heights of those impulses are going to be the values of the samples. So we're going to stay in the analog domain here, dealing with kind of weird signals. They're going to be impulse trains. But for now, that's how we're going to represent the sampled signal. So how do we do that? Well, we do it by using the sampling property of the impulses. We're going to take our x of t and multiply it by this periodic impulse train, the sampling train of impulses. So if you look at what this is going to be a train of impulses, unit impulses, that are located at integer multiples of some time capital T. So they're separated by capital T. That's what we refer to as the sampling period. We're sampling the signal every capital T seconds. And the way we do that is we multiply by this impulse train. And when we do that, we end up with, of course, we call that P of T. And we just multiply our signal by P of T. So, let me just go down a little. So here's P of T, the impulse train. I multiply my signal that I'm sampling by P of T, and that's all I've done here. It's x of t times this summation. And now I can just basically do it term by term in the sum. And I know that when I multiply my signal x of t by the impulse, it gives me an impulse located at the location of this delta function, which is located at n times capital T. And the height of that impulse is just the value of my signal at that point. So I end up with the sum of x of nt, n times capital T, times delta of t minus n times capital T. So what is this? This is exactly a train of impulses separated by the sampling period. And at the time n times capital T, the height of that impulse is just the value of the signal there. It's x of n times capital T. So you can think of this I call it x sub p of t. So it's the continuous time sampled signal. It's just a train of impulses that you can think of as bounded by the envelope x of t. So let me just show you a picture. Okay, so here's my original signal x. I multiply it by the sampling train. We said that using the sampling property of the impulse signal, we end up with this. We call that x sub p of t. So in figures, here's my original x. This just means multiply. It's not any fancy tensor operation. It just really means multiply these two signals. I'm going to multiply it by the sampling train. So here's one impulse at 0, another at capital T, another at capital 2T, and so on. And what do I get when I do that? I get something that looks like this. This is the product. Get that down there. This is the product. Let me just scale it down a little bit. So I'm just multiplying this by this. And you can just think of it as now that signal X becomes sort of the envelope for these impulses. These are still located at 0, T, 2T, 3T, but their heights are X of 0, X of capital T, X of capital 2T, X of 2T, and then X of 3T. Okay, so that's what we do when we sample in continuous time. It's not, what are we going to do, by the way, when we convert it to discrete time? We're going to take those pointy arrowheads and we're going to convert them to circles so that they become stems. And then the axis here will just be the index, 0, 1, 2, 3. Okay? That's all we're going to do. But for now, keep it the continuous time domain because we don't know how to do transforms yet for discrete time signals. But we do know how to do transforms for this kind of signal. This is a perfectly legitimate, this sequence of impulses is a perfectly legitimate continuous time signal. We ought to be able to figure out its Fourier transform. And that's what we want to do. So remember what we did was we took our X of t and we multiplied it by the impulse train. So let's first look at our signal X of t in the frequency domain. So we take X of t, we do the Fourier transform, and we get, this is just an arbitrary drawing. You know, this is actually the transform of a sinc squared, which is not what this looks like. But just think of it as being a band-limited signal. So it has kind of a maximum frequency W, where the transform is 0 for frequencies bigger than W and 0 for frequencies that are less than minus W. So that's our signal transform. We now multiply it by this impulse train, the sampling train. Well, this is our picket fence in time. We know that it transforms to a picket fence in frequency. And what is it? Well, they're separated by the fundamental frequency. Well, the fundamental frequency of this period t impulse train is 2 pi over t. So these are going to be separated by 2 pi over t. And their height, because the Fourier series of this guy is 1 over t at every value, that rule for constructing the Fourier transform of periodic function, which this is, periodic signal, just gives us height 2 pi over capital T. So now we have the transform of our signal, x of j omega. We have the transform of our impulse train, p of j omega. How did we get our sampled signal? We multiplied them. So we're actually going to use the exact same property we used in the amplitude modulation application. We're going to use the multiplication property. And the multiplication property tells us that to get the transform of that sampled signal, x sub p, that's going to be capital X sub p of j omega, well, we're going to apply the multiplication property to the definition of x sub p of t, which is that it's x of t times p of t. And what does that multiplication property say? It says multiplication in the time domain becomes 1 over 2 pi times convolution in the frequency domain. So x sub p of j omega is going to be 1 over 2 pi x of j omega convolved with p of j omega. Now that's actually not such a difficult thing to figure out because remember what p of j omega is. P of j omega was itself an impulse train in the frequency domain, right? P of j omega was this guy. Well, we know how to convolve anything with a time shifted, in this case it's a frequency shifted impulse. We just take the thing that we're convolving with that impulse and we plop it down right where that impulse is located. And so that's all we end up doing. here to get our transform. We want to have x of j omega convolved with p of j omega. Well, these blue arrows here, those are the impulses in the p of j omega. We're going to convolve x of j omega, which I'm representing as this band-limited function of frequency. And all I do is I make copies of it. I just add up. I have to add those copies up, but I basically place a copy centered at each one of those, and then I'm going to add those things up. And the result is going to be the final transform of my sampled signal. So notice what it looks like. In this particular instance, I placed my, I chose my sampling frequency, 2 pi over the sampling period, just right so that my copies of the x of j omega didn't overlap. They just kind of touch at the base. And so what I ended up with was a bunch of an infinite string of copies of my x of j omega. And so the whole idea of sampling theory is going to be that if I choose this sampling frequency big enough so that these copies don't overlap, so I'm going to have nice, clearly visible, distinguishable copies of my x of j omega, but just there'll be one centered at 0, but then there'll be one centered at the sampling frequency and another one centered at 2 times the sampling frequency. But I'm going to have that one sitting centered at 0 frequency, just like in the amplitude modulation. When we did that demodulation step, we ended up with a copy. It was scaled by a factor of 2. We ended up with a copy of the thing we wanted sitting right there, centered at 0 frequency. And we just applied a low-pass filter, and out it popped. So it's going to be the same idea here. If they're separated enough, we can stick in a cutoff frequency for a low-pass filter. All this extraneous stuff, all those infinite number of copies on the wings, just like over here, they're going to go away. And all we're going to be left with is our nice copy of x of j omega sitting in the middle. So that'll be the frequency domain picture of the output of our reconstruction filter. Well, if that's what it looks like in the frequency domain, if it looks like x of j omega in the frequency domain, that means in the time domain, that signal is just x of t. We've reconstructed our signal. So that's the key. So you can kind of see that there is going to be those two requirements, that x of t be a band-limited signal, that it have a maximum frequency, because if it didn't have a maximum frequency, then there's no way you could avoid those copies overlapping. And so you wouldn't have a nice, clean, unadulterated copy of x of j omega sitting there ready to be filtered out by the reconstruction filter. So you need x of j omega to have this finite bandwidth, but you also need to have that sampling frequency big enough, right? And the separation of these guys is the sampling frequency. You want it big enough so that they're separated so that those copies don't overlap. And those are what those two conditions are all about. And in fact, you can see even from this, you can kind of get the idea that the size of that sampling frequency should be 2 times the max frequency, right? Because the max frequency is from 0 to that edge. So you want to have that separation big enough that you go from 0 to the max frequency. And then over here, where you're going from the sampling frequency minus the max frequency, you don't want that to be overlapping with this. So you want that separation to be at least twice the maximum frequency of the signal. Okay. So this is the gory details. Okay. This is the gory details of writing out that calculation, but we don't have to do all that. We know that when we convolve x of j omega with p of j omega, we don't have to really write out the convolution because we already know. We showed that when you convolve with an impulse, you just move your thing over to the location of the impulse. So our impulses are at multiples of 2 pi over t. So all we do is we take a copy of x of j omega and we park it over at 2 pi k over t. for each k. So if you want to go through all the details of the convolution, you can, but we kind of already did that. For impulses, we don't have to repeat it. We just get this sum of frequency-shifted copies of x of j omega. And then, of course, the 2 pi over t, that was the coefficient over here for those impulses. In the multiplication formula, we have 1 over 2 pi. The 2 pi's actually disappear, and we just have 1 over t. So what we get is we get that those copies of x of j omega, I didn't go through that particular detail here, those copies end up being, A was the maximum magnitude of x of j omega. In those copies, the magnitude is going to be A divided by t. So just like in the amplitude modulation, we had to scale up by a factor of 2 because when we demodulated, we ended up with that factor of 1/2 showing up. Here we end up with a factor that depends on the sampling period. It's 1 over t. So our reconstruction filter, instead of having a gain of 2, is going to have a gain of t. It's going to have a gain of t to get that amplitude back up to where we want. Otherwise, we'll end up with our signal, but it'll be reduced in volume by a factor of capital T. This was our continuous time sampled signal. So we multiplied it by the impulse train, and we get this kind of varying height train of impulses. And the transform turns out to be just like this. The copies are separated by 2 pi over t. They're added up. I'll show you an example in a minute where they aren't separated enough. And what you get there, does everybody know what term applies when you don't sample at a high enough rate? We've kind of talked about this earlier. It's aliasing. It means you didn't sample at a high enough frequency. And bad things happen then because these copies overlap. So you don't have this guy just sitting there ready to be plucked out by your reconstruction filter. Okay. So this is the frequency domain picture of that time domain sampling. And this is just to emphasize the fact that as t increases, let's see. So t is increasing. So here, just to make sure it's clear what this is, these are sampling trains. So this is the first one where you're sampling at capital T. Here's where you're sampling at, I probably should have called this T prime. It's a bigger value of T. So you're sampling farther apart, which means, even intuitively, it kind of means you're not getting as good a snapshot of your signal. So when you look at 2 pi over T, for the smaller value, the separation, this is now in the frequency domain, the separation of those copies of x of j omega is going to be bigger than if you sample too far apart. Because when t is bigger, 2 pi over t is going to be smaller. And those copies now are too close together, and they're going to start overlapping, and you're going to end up with this phenomenon of aliasing, which is kind of depicted here. This is where you had a sampling period. Let's see. This is, this is wrong. This is if 2 pi over t is too small. So if t is too large, the sampling period's too large, the copies will overlap. So this was a small sampling period. So 2 pi over t is big. They're separated. This is where t was too large. So 2 pi over a large number is going to be small. And now you get this overlapping. And so you can see when you go in and try to do the reconstruction, you're not going to get a nice clean copy. Because remember, these are adding up. So when you add up, I think I have a picture here of when you add up, you end up, let's see, do I have a picture? I thought I had a picture here. Sorry. Yeah. So when they add up, you end up with something like this. So you can see you don't see your nice triangular x of j omega anymore. You've got this funny business in the tails, which means that when you do a reconstruction, you're kind of out of luck. You don't have x of j omega anymore. You got some distorted version of it. Okay, so that's how the sampling period relates to the reconstructibility. Now, are there any questions on that? Yeah, I think if you look at that and kind of think about it, you do have to think a little bit carefully about the relationship between them. And so here's the final upshot. This is the sampling theorem of Shannon and Nyquist. So you let x of t be a band-limited signal. So that means x of j omega is 0 for frequencies larger than w in magnitude. If you sample at a rate we usually call the sampling frequency omega sub s, that's going to be 2 pi over capital T, where capital T is the sampling period, the sampling interval. Then no aliasing will occur provided that omega sub s, the sampling frequency, is at least twice the maximum frequency in the signal. Now, it's very helpful to kind of relate that back to what that frequency domain condition, which kind of popped out of the pictures, how that translates into a statement about the sampling period. What it tells you is your sampling period has to be smaller than pi divided by w. That just follows from the fact that omega sub s is 2 pi over t. So omega sub s is at least twice w, and the sampling period t is no bigger than pi divided by w. And if you do that, if you sample that way, then you can reconstruct the signal x of t from its samples using that reconstruction filter. Okay, so everybody's comfortable with that? We basically proved that theorem just now with our analysis and our pictures. Now, I want to tell you one more thing that's kind of interesting about this reconstruction process. We've looked already at the frequency domain perspective. This is just kind of repeating what we just said. I want to just say a word about the time domain view of the reconstruction process. So you remember what we had. We have our sampled signal. It's this sequence of this train of impulses whose heights correspond to the value of the signal. And we saw that in the frequency domain, the transform of that was these copies of x of j omega, repeated every multiple of the sampling frequency. The question is sort of what's happening in the time domain. We run that thing, that x sub p of j omega, we run that through this filter, and we saw that what we get out basically looks in the frequency domain like x of j omega, and therefore in the time domain it's x of t. But the question is, what's really happening here? X sub p of t is that sampled signal. X sub p of t is that signal that we got by multiplying by the impulse train. And we're taking that signal. We've kind of looked at everything from the frequency domain. But let's look back in the time domain. We took our x of t, we multiplied it by p of t, and we got this x sub p of t, our sampled signal. And that's the thing that kind of looked like this. And we said, provided that we picked t to be small enough compared to the bandwidth of our signal, that when we run that thing through our reconstruction filter, h of j omega, and that in the frequency domain looks like this, that what we get out is our x of t again. Well, we can look at this in the time domain, right? What do we know about putting something through a filter? What's this output over here? This output is x sub p of t convolved with the impulse response of our reconstruction filter. Well, if that's ideal low-pass filter is represented by that rectangular pulse, what's the inverse transform of that? It's a sinc function. So what that's telling us is that somehow or other, magically, when we convolve this with a sinc function. Now, what does that mean? We're convolving with a bunch of impulses. That means we put a sinc function at each one of these points. We put a sinc function at each one of those positions, scaled by the height of that impulse. And when we add up those sinc functions, we magically get x of t back. Right? So here's the inverse transform of h of j omega. Remember, the reconstruction filter had amplitude t, magnitude t. That's our sinc function. That means that when we multiply this guy, x sub p of t, we not multiply, convolve it with that sinc function, somehow or other, everything adds up. Right? Here's the sinc function shifted by capital T, scaled by the value of the signal, shifted by nt, scaled by the value of the signal nt, and you add those up, and somehow magically, it adds up to x of t. Amazing, isn't it? Who would have thought, right, that that's the way you'd get the signal back? Okay, so that's the time domain view of sampling theory.